In this lesson, we're going to talk about the graphs of the sine and cosine functions. So previously, we've been looking at sine and cosine as being functions that, take an angle as an input and give us a ratio back. And now we're just looking at what the graphs of these things look like. So before I get into that, I sort of want to remind you of what to expect about these graphs. When I say y equals sine x, if I'm going to be graphing this, it effectively means that our x-axis and our y-axis actually represent something now. The x-axis effectively represents the angle that we're working with. By the way, when we're doing graphs, this angle is always going to be done in radians. I know for the past few lessons I've been bouncing back and forth between radians and degrees and saying, they're both useful in different times. Degrees are barely useful in graphs. In fact, I'm just going to say they're not useful. A part of the reason we need to do so much with radians is that when you're working with a real function in calculus, that thing needs to be in radians. So expect your x-axis to effectively represent radians and effectively be the angle. Your y-axis then is going to be the ratio that you're looking at, right? It's going to, you're looking at the sine ratio. And this is going to be true for both sine and cosine. So with that said, let's move on and take a look at what the sine graph actually looks like. So this is the graph of y equals sine x. On the one hand, memorize it. Things that you need to memorize. Notice that it starts at the origin here, and notice that the graph effectively repeats itself over here at 6.28 at 2 pi. And now that I think about it, I should have shown more of this graph. Understand that this wave shape that happens here ends up repeating again over here, and it's going to keep repeating itself over and over and over again, as we go on to the right, and that should make sense. I'd really like you to take a minute and think about, surprise, surprise, think about the unit circle. That's a terrible circle, but we'll deal with it. And think about how this graph totally makes sense. Imagine that as you're going across the x-axis, you are just increasing your angle as you're going along, right? So imagine that here you are in the unit circle, and you start going around the unit circle. Think about what the sine values are as you start out. You start out with 0, then your sine values get larger and larger and larger, up to a maximum of 1 at pi over 2. Well, sure enough, that maximum of 1 happens right here at pi over 2. Right? As we continue along around the unit circle, these sine values begin to get smaller and smaller and smaller until we hit a sine value of 0 over here at pi. Notice that over here, my y values are getting shorter and shorter and shorter until I hit pi, where I'm at 0. Right? As I continue around the unit circle, I now get larger and larger negative sine values. Sure enough, here I'm getting larger and larger and larger negative y values until I hit negative 1 here at 3 pi over 2. And finally, my negative y values get smaller and smaller and smaller. Well, less and less negative as I come back up to 0 here at 2 pi. But then imagine, what happens as x keeps going? It just means you keep going around the unit circle, and this pattern of values just repeats itself, and you're going to get this same sine wave shape again and again and again as you follow this graph out to the right. So this is the graph of sine. You should memorize it. We need to have it in our minds, and it needs to be very clear to us. But at the same time, I don't just want it to be a blind memorization. I want you to understand this graph totally makes sense given what we know about the unit circle. So here I have the graph of cosine. Notice that this one doesn't start at the origin. This one starts out at 0, 1, and that should make perfect sense. If you imagine the unit circle, when you are at an angle of 0, your cosine value is 1. Right? Remember that with cosine you're looking at the x-coordinate on the unit circle. So if I was looking at these x-coordinates, I start out at 1, and I get steadily smaller and smaller positive x values. Sure enough, these values are getting smaller and smaller and smaller until I hit 0 at pi over 2. And you can sort of see these key values. There's pi over 2, here's pi, where the cosine is negative 1. Sure enough, that cosine value is negative 1 here. As I go around again, my cosine value comes back to being 0 here at 3 pi over 2. Sure enough, right here at 3 pi over 2, my cosine value is 0, and then it ends up back up here at a maximum when I get over to 2 pi. Right, so once again, the graph of cosine completely repeats itself between 0 and 2 pi, so the shape that you have here of the cosine curve is exactly the same as you go on and repeat it between 2 pi and 4 pi, because we could just keep wrapping around the unit circle again and again and again. So I don't want to spend as much time talking about cosine as I did sine, but just understand the graphs of sine and cosine, very simple, very similar looking graphs if you think about it, but they start in different places and they're just a little bit different from one another. I'm going to spend a little bit more talking about the similarity between the sine and cosine graphs in a future lesson, probably the one for tomorrow, but there's those graphs. But of course, there's still more left to the video. Just like any other graph, these graphs can totally be translated and stretched and moved around. I hope you guys remember, with parabolas. You guys, back in intermediate algebra, y equals x squared, we knew that was just a parabola centered at the origin. If I give you something like y equals 4x squared minus 5, we knew that just meant a parabola was shifted down 5 units. 5, and then was sort of steeper than usual because of the 4. That same idea is going to be used here, right? So if I ask us to sketch the graph of y equals 3 sine x plus 2, we recognize that this number on the end represents a vertical shift, right? And we recognize that this 3 basically represents a vertical stretch. And in trig, in periodic graphs and things like that, that 3 is a number that's referred to as the amplitude. And technically it's the absolute value of whatever was there, so if that had been like -3, the amplitude would still be 3. So this graph is an amplitude of 3, which basically means with the sine graph, instead of going up to 1 and down to -1, this graph is going to go up to 3 and down to -3. It's going to be stretched to be 3 times taller. So again, instead of just, if you remember your original sine graph, and I'll just sketch it here really quickly, remember the original sine graph basically looked like this. It started over here at 0, it ended over here at 2 pi, it went up to a maximum height of 1, down to a minimum height of -1. Our graph here is going to go up 3 and down 3, and then on top of that, it's actually going to be shifted up by 2 units. Right? So when we draw this graph, we sort of understand it, and what I usually like to do in these graphs is I like to sort of pinpoint key values. So here's 0, here's pi, here's 2 pi, here's pi over 2, and here's 3 pi over 2. And it's almost like we knew that our original graph was supposed to start here, go up to 1 by this point, down to -1 by this height. We sort of had a few values pinned in there, right? So what's going to happen here is this graph, first of all, and I'm probably going to run out of space here, this might get messy. First of all, I know my graph is supposed to start at 0, it's supposed to go up 3 units, so 1, 2, 3, it's supposed to be up 3 units by here, back to 0 here, it's supposed to be down 3 units over here at 3 pi over 2, and then back up to 2 pi here. So you can sort of imagine just the 3 sine x part would do this. Right? So it's a sine graph shape, but it's 3 times taller. Right? But I then have a vertical shift of 2, which means every point I had moves up by 2 instead. Right? So I'm looking at this graph actually starting here, and then I like to think about this amplitude and say, okay, from that point, I'm going to be going down 3, and my graph will not be going below this. And that's not really an asymptote, but I'm just drawing. It's not going to go below that. Above that, it might go up as far as 1, 2, 3. So this is sort of the highest that this graph is going to go. And so from there, I can sort of fill in. From here, it's going to go up to that maximum value. Then it'll go back down to the equilibrium point by the middle there. It'll go all the way down to my minimum value here, and then it has to come all the way back up to equilibrium by the time I get to 2 pi. Right? By the way, when I talk about equilibrium, usually the x-axis is sort of equilibrium at sort of the, the ground level of the function. I'm basically just saying that in this graph, my ground level had been shifted up by 2, right? So I've got this graph, keep in mind it sort of keeps going in both directions, but that's what this graph is going to look like. Now that may have been slightly confusing. I think I've got 2 more examples lined up, so we'll take a look at those next. So for this one, I'd like us to sketch the graph of -2 cosine x plus 3. So first of all, it's good for us to remember what just the graph of y equals cosine x looks like. Cosine starts out up at 1, drops down, and then comes back up by the time we get over here to 2 pi. So that's what the normal cosine graph looks like. Okay. So for us, we need to do a vertical shift of 3, and we need to do a vertical stretch of -2, right? So I'll sort of draw a whole graph here. So I'll try and be a little bit more clear about my steps on this one. I like to deal with a vertical shift first, right? So I almost like to think about what happens to the origin. The origin, in other words, sort of the equilibrium line, effectively gets moved up by 3, right? So if I go up 3, this is sort of where my new equilibrium is. This is the line that cosine is going to go and sort of be focused around, right? So now normally cosine would start out up 1 and then work around it. But because this is multiplied by -2, I'm going to make it 2 times taller, which means it's going to go sort of up by 2 potentially and down by 2 potentially. And then on top of that, because it's -2, my graph shape is actually going to be upside down. So rather than start out up at the top, it's actually going to start out down here, right? So the next thing I do is I sort of plot out my key values. And if possible, it's nice to keep some semblance of scale here. So if we look at this, this is 1, 2, 3, 4, 5, 6. So sort of that distance is sort of 6-ish. So that means that, that rough distance is sort of how long your 2 pi should be. So I'm going to say right about here is where 2 pi is. That means in the middle is where pi is. In the middle of that is pi over 2. And in the middle of those two is 3 pi over 2. And so now this is where we can sort of match the graph to this shape. Right? So from here, we sort of get back to equilibrium by that point. I go up to the top by the time I get to pi, down to 3 pi over 2 for that one, and then back down to the bottom for 2 pi. Right? So that's the shape of this graph. And as I've mentioned before, if that was 2 pi, then this is where 4 pi is. That same shape will get repeated over and over again. Right? Usually when I have us draw these, we're only going to draw like one period of the graphs, but it's good to know that it's, these graphs don't stop at some point. They actually keep going in both directions, for infinity. So I have one last question, and that is, what are the minimum and maximum values attained by that function? And I kind of want you to think about the graph, but I don't necessarily want you to graph the entire thing to answer this question. So pause the video, think about that for a minute, see if you come up with anything. So my thought on this is effectively, and I know I said don't graph the thing, so don't graph it, but let's at least give some thought to how we would start this. Our first step is to plot equilibrium, right? So we sort of go down to -4. So this is sort of the equilibrium line that sine is going to be going above and below, right? Then you've got -7. So what does that mean? That basically means that the amplitude of your graph, the amplitude of this function is 7. In other words, this graph is going to go 7 further down, so that puts us down here at -11, and then it's going to go 7 above that, 1, 2, 3, 4, 5, 6, 7. In other words, up here to 3. Right? And in some sense, that's it. I don't need to answer any more of this because I recognize this graph is going to go down to a minimum value of -11 and up to a maximum value of 3. Right? For those of you that kind of want to know, this graph would start out going down and then up and then back down again. this graph is totally not to scale because this is 0 and this is, 2 pi. So, technically this is 6.28 units, but that 6.28 looks, I don't know, maybe it's not horribly not to scale. At any rate, that's what the graph would look like, but this was the computation of the minimum and maximum values that we found. So hopefully that makes sense. In the next video that we have, I'm going to be looking at the graphs of the other 4 trig functions, which my descriptions really depend on your knowing the sine and cosine graphs pretty clearly. So please make sure that you've got the basic graphs of sine and cosine sort of memorized, or at least well in your minds, before you go on to the next video. I'll see you there.